So, hi everyone. Now, in today's video, we are going to talk about combination of capacitors. Okay, like suppose you have some capacitors. Okay, this is one capacitor. This is another capacitor. Okay, you have several capacitors. Now, these capacitors can be combined. Combined means they can be connected uh, in several ways. Okay, now one way is the series combination. Series combination. And the other one is parallel combination. Okay, now this is the simplest form. Okay, there are complex forms also where you can have both series and parallel. Okay, and then again in some combination where the capacitors might not be in series or in parallel, but some other combination, then we will be asked to solve such combinations also. Okay, but this is the most fundamental form of combination: series combination and parallel combination. Okay, now first let us see series combination. Okay, series combination. Now suppose you have three capacitors. Now series combination means they will be connected like this. C1, C2, C3 are the capacitance. Okay, and this combination, it is connected with a battery. Okay, so this is the battery which is supplying at potential at V volt. Okay, acha. Now this is the path through which the charges will go. So suppose Q charge is supplied by the battery. Okay, so this charge will go through C1. Okay, it will go through C1, then through C2, and then through C3, and finally it will travel like this. Okay, so that means all the three capacitors will have same charge. Okay, see, while going from, suppose this is A and this is B, so while going from A to B, it has to cross all the three capacitors. Okay, so there is only one path available from A to B. So that means all the capacitors will have same charge. Okay, so this is the condition for capacitors to be in series. Okay, for capacitors in series, for capacitors in series, all the capacitors will have same charge. Same charge. Okay. Achha. Now, see, what is the relation between charge, capacitance, and potential? Q is equal to CV. Q is equal to CV. Okay. Now, all the capacitors, they are getting same charge. Okay. So that means here this charge is constant. For all the capacitors, this will be same. Now, since C has different values, okay, here for three capacitors, we have capacitance C1, C2, and C3. So since capacitance are different, potential drop will also be different. So let us take V1 is the potential drop across C1, V2 is the potential drop across C2, and V3 is the potential drop across C3. Okay. So that means of the total potential V is the total potential drop, correct? Across this combination. So this V is divided into two parts as V1, V2, and V3. Okay, so out of this V1 is dropped across C1, V2 is dropped across C2, V3 is dropped across C3. Okay, acha. Now we have to find the equivalent capacitance of this combination. Okay, now let us replace this circuit, above circuit, with a single capacitor of capacitance CS. CS means capacitance in series. So CS is basically the equivalent capacitance for C1, C2 and C3. Okay, so C1, C2, C3 is replaced by CS, and this is the same circuit. So we have the same potential V, and this is supplying charge Q. Okay, so now this CS capacitor with capacitance CS will get charge Q. So for this I can write Q is equal to CS into V. Okay, so that gives V is equal to Q by CS. V is equal to Q by CS. Okay, suppose this is equation 1, this is equation 2. Okay, acha. Now what is V1? What is V1? See, V1 is the potential drop across C1. Correct? V1 is the potential drop across C1, and C1 is getting charge Q. Okay, so I can write V1 is equal to Q by C1. Similarly, V2 is equal to Q by C2, and V3 is equal to Q by C3. Okay, so this is equation 3. Suppose this is not equation 3 actually. It's combined, this all the three combined, let us this be 3. Okay, so I can substitute the value of V1, this V1, V2 and V3, that can be put here. Okay, so what do we get? We get this V is Q by CS. Okay, so Q by CS is equal to Q by C1 plus Q by C2 plus Q by C3. Correct? So this Q gets cancelled. Okay, Q gets cancelled. So what do we get? We get 1 by CS is equal to 1 by C1 plus 1 by C2 plus 1 by C3. So what is CS? CS is the equivalent capacitance of C1, C2 and C3. And how C1, C2, C3 are connected? They are connected in parallel. They are connected in parallel. Sorry, they are connected in series. Okay, so this is for series combination. This is for series combination of capacitors. So this is similar to your formula that you used for resistors in parallel. Okay, in resistors, if R1, R2, R3 are connected in parallel, equivalent resistance was 1 by R1 plus 1 by R2 plus 1 by R3. Okay, so that same formula here for capacitor we are using. Okay, so this obviously, see, suppose, so this is the final result. So let us analyze this result a bit more. So suppose you have two capacitors. One is 2 microfarad and the other one is say 4 microfarad. Okay, now they are connected in parallel. They are connected in parallel. Okay, so this is 2 microfarad and this is 4 microfarad. So what is the equivalent capacitance? Equivalent capacitance, C equivalent or 1 by CS, it will be 1 by 2 plus 1 by 4. 1 by 2 plus 1 by 4. Okay, so 1 by 2 plus 1 by 4, half plus quarter. So this is 4, 2 plus 1. So this is 3 by 4. So that means C equivalent, it will be equal to 4 by 3. Okay, 4 by 3 means this is somewhere 1.33 microfarad. Now this 1.33 is less than 2 and it is also less than 4. Correct? So that means in series combination, the equivalent capacitance will be less than the individual capacitance. Okay, so if you have a capacitor of capacitance 2 and 4, now when they are joined in parallel, the net capacitance will be less than 2 and it will also be less than 4. Okay, so this is one important observation. In series combination, in series combination, the equivalent capacitance is always less than individual capacitance. Individual capacitance. Okay. Now, another thing, see, suppose you have two capacitors of capacitance C1 and C2. Okay. And this is connected with a source of potential V. This is connected with a source of potential V. So here the potential drop is V1. Here the potential drop is V2. Both are getting same charge Q. Both are getting same charge Q. Okay. Acha. So if you have to find the value of Q, see, Q is equal to C equivalent into V. V is the total potential drop. Okay. Now suppose this circuit is replaced by C equivalent. Okay. So this is battery of potential V and it is supplying Q. So Q is equal to C equivalent into this Q. It is equal to C equivalent into V. This relation. Okay. Now what is C equivalent? 1 by C equivalent is equal to 1 by C1 plus 1 by C2. So that gives C equivalent is equal to C1 C2 divided by C1 plus C2. So that gives Q is equal to C1 C2 divided by C1 plus C2 into V. Into V. So this will be the charge supplied by the battery. This will be the charge supplied by the battery. Okay. Another thing is, see, in the relation Q is equal to, see here, both the capacitors are getting same charge. Okay. So that means Q is equal to C1 V1 and Q2, not Q2 actually, Q is equal to C2 into V2. Okay. So capacitance and potential is changing. Q is constant. Q is constant. So if Q is constant, we can say that this C1 is inversely proportional to V1, or I can say V1 is inversely proportional to C1, C1, and V2 is inversely proportional to C2. Correct? So I can write V1 by V2 is equal to C2 by C1. V1 by V2 is equal to C2 by C1. Acha. Also, see here this V V is divided into V is divided into V1 and V2. So that means sum of V1 and V2 is equal to V. Sum of V1 and V2 is equal to V. Okay. So that is another useful relation. Also, we have V1 plus V2 is equal to V. V1 plus V2 is equal to V. So that means if I use these two relations, I can write V1 is equal to VC2 divided by C1 plus C2, and V2 is equal to VC1, V times C1 divided by C1 plus C2. Okay, so see here, if C1 and C2 is known, okay, C1 and C2 is known, V is known, we can find the potential across each capacitor. we can find the potential across each capacitor. Okay, let me show you one example. Like if you know this formula, see, suppose you have one capacitor, another capacitor, they are in series connected to a potential source. Now here V is equal to suppose 4 volt. Okay, and suppose this is C1 is equal to 4 microfarad and C2 is equal to 8 microfarad. Okay, and you are asked to find V1 and V2. V1 and V2. So using this formula, we can directly find the value of V1 and V2. Okay, because V and V, C1 and C2 are only known required. Okay, if V, C1 and C2 are these things, V is 4 volt, C1 and C2 is also given. So using that, we can find the value of V1 and V2. Okay, so this is about series combination. Series combination. Okay, now next, let us see capacitors in parallel. Capacitors in parallel. Okay, so suppose you have this one capacitor, this is another capacitor. Okay, now this is, they are in parallel and this is connected to a battery of potential V. Okay, so across the battery, the potential difference is V. Okay, suppose this is C1, this is C2. So across C2, potential difference is V. Across C1 also, potential difference is V. So here, across both the capacitors, potential difference is same. Okay, so that means when capacitors are in parallel, potential across them, potential difference across capacitors in parallel is always same. Okay, so now we have got two things, important things. One is when capacitors are in series, they will have same charge, and when capacitors are in parallel, they will have same potential. Okay, same potential. Acha. Now suppose this battery is supplying charge Q. Okay, so Q1 is the charge going to C1, Q2 is the charge going to C2. So I can write Q is equal to Q1 plus Q2. Q is equal to Q1 plus Q2. Okay. Now suppose for this circuit, the equivalent capacitance is this one, CP. CP means capacitors in parallel with the battery, same battery. Now this is supplying charge Q. Okay. So for this combination Q, CP, V, I can write Q is equal to CP into V. Okay. Acha. What is Q1? Q1 is the charge on C1 where potential is V. So I can write Q1 is equal to C1 into V and Q2 is equal to C2 into V. Okay, so if I substitute this, so I get, what is Q? Q is CPV. Q1 is C1V plus C2V. Okay, so C1, this is V. Okay, V. So all these V gets cancelled. All this, okay, this is, let me write it again. Actually, see, this is Q, this is Q. So this Q is CP into V. Q1 is C1 into V plus C2 into V. So this V gets cancelled. So CP is equal to C1 plus C2. Now this formula is similar to for resistors in series. Okay. So what is happening? The formula is getting jumbled, parallel and series interchange for capacitors and in resistors. Okay. So CP is equal to C1 plus C2. Okay. Now suppose you have one capacitor of 2 microfarad and another capacitor of 4 microfarad. Okay. This is in parallel. So here the equivalent capacitance Cp will be equal to 2 plus 4. So that is equal to 6 microfarad. So now 6 microfarad is greater than both 2 and 4. It is greater than 2 and 4. So here the capacitance is equivalent capacitance is greater than the individual capacitance. Okay. Equivalent capacitance in parallel is always greater than individual capacitance. Okay, now this is just the opposite to what we got in series combination. The equivalent capacitance is always less than the equivalent capacitance. Okay, so here it is greater, here it is greater. Okay, acha. Now another thing is, see, you have a capacitor, suppose this is C1. This is another capacitor of capacitance C2. Now this is connected to battery. Okay, now this is getting charge Q1, this is getting charge Q2. Okay, across both potential is same, V. Okay, now in the relation Q is equal to CV, here V is constant, here V is constant. So that gives Q is directly proportional to C, directly proportional to C. Okay, now so that means I can write Q1 is equal to, see, Q charge is supplied, so Q1 will be equal to QC1 divided by C1 plus C2. Okay. Similarly, Q2 is equal to QC2 divided by C1 plus C2. So from this you can find the charge on individual capacitors. Okay. So here in parallel combination, charge is divided. Charge is divided in the ratio of capacitance. Charge is divided in the ratio of capacitance. Okay. And in this series combination, here this is a series combination. So here this charge potential is divided, V1 and V2. V1 and V2 are the potential. So here potential is divided in the inverse ratio of the capacitance, because potential is inversely proportional to capacitance because charge is constant. Okay, so this is one important result or observation we can say, based on the concept of series grouping of capacitors and parallel grouping of capacitors. Okay, Acha. Now based on this, let us solve one question from your this NCRT textbook. Okay, NCRT question. This is question number 2.25, 2.25, page 90. Okay, so you basically, what is given is, you are given a circuit of capacitors. So this circuit is given. Okay, now this is the potential source, and this is 300 volt. Okay, this is positive terminal, this is negative terminal, and this is capacitor C1 of 100 picofarad. This is C2 of 200 picofarad. This is C3 of 200 picofarad, and this is C4 of 100 picofarad. Okay, now what is asked? Obtain the equivalent capacitance and determine the charge and voltage across each capacitor. Okay, so first we have to find the equivalent capacitance. Okay, so see, if you see the circuit, this 200 microfarad, 200 picofarad and 200 picofarad. Now they are in series. They are in series. Okay, so the equivalent capacitance of this part is 200 and 200. 200 picofarad. This is 200 picofarad. Okay, so equivalent capacitance for them is 1 by C is equal to 1 by 200 plus 1 by 200. Okay, so that will be equal to 2 by 200. So that is equal to 1 by 100. So that means C is equal to 100 picofarad. Okay, so that means this circuit can be redrawn as the top one 100 picofarad, then this 200 becomes 100, so 100 picofarad. Here you have C4 as 100 picofarad, and then we have the battery here. Suppose this is a positive terminal, this is negative terminal, so this is 300 volt, 300 volt, 300 volt. Okay, now this circuit can be further this simplified, because these two capacitors, they are in parallel. Okay, they are in parallel, so their equivalent capacitance will be 100 plus 100, that is 200. Okay, so this circuit, let me take this to a new page. So this circuit can be further redrawn. This 100 combined becomes 200 picofarad. This is 100 picofarad, and this is the battery. This is the battery, 300 volt. Okay, now this 200 and 100, they becomes in series. So the equivalent capacitance C equivalent will be equal to 1 by 100 plus 1 by 200. So that is equal to 200, 2 plus 1. So that means C equivalent is equal to 200 by 3 picofarad. 200 by 3 picofarad. Okay. So this is the equivalent capacitance. Okay. Now, what about the charge? What about the charge and the voltage across each capacitor? Charge and voltage. Okay. See, here this 100 and 200, they are, see, C equivalent is 200 by 3. C equivalent is 200 by 3. Okay. So if Q charge is supplied, Q charge is supplied. Okay. So what is the value of this? What is the value of this Q? Q will be equal to C equivalent into voltage. So that means Q is equal to how much? Q is equal to C equivalent is 200 by 3. 200 by 3 picofarad, that is 10 power minus 12, multiplied by voltage, that is 300. Okay, so this is 300 times. Okay, so Q is equal to this is 2 into 10 power minus 8 coulomb. So this is the charge supplied. Okay, this is the charge supplied. So 100, this is the charge. So this charge is going from this path. So this is 2 into 10 power minus 8 coulomb. Okay, so this charge will go through this 100 microfarad or picofarad. It will reach this point. Now these two capacitors are identical. They are in parallel. Okay, this 100 picofarad and 100 picofarad, they are in parallel. Capacitance is same, potential is also same. So that means they will get same charge. Okay, they will get same charge. Correct. So this 100 picofarad and this 100 picofarad, they will get the same charge. Okay, so that means this charge Q will be divided into equal parts. So this capacitor will get a charge of 1 into 10 power minus 8 coulomb. This will also get a charge of 1 into 10 power minus 8 coulomb. Okay, now since charge is known, we can find the potential across each capacitor, because Q is equal to CV. So V is equal to Q by C. So if you know charge on each capacitor, you know the capacitance. So you can very well calculate the potential. Okay, so please do complete this solution on your part and send me the solution. Okay, if possible. And if there are any difficulties, do let me know so that I can help you. Okay.